All right, in this video, we're going to talk about how do you change momentum. So we imagine a stone rolling down a hill, right? We have the stone and it's rolling down the hill, right? So at the bottom of the hill, you need to stop the stone. So how do you stop it? Well, to stop the stone or change its momentum, you will have to apply a force on the stone, right? So in order to change momentum, it takes a force. And that leads us to a second equation in this unit, and it's part of a theorem here. This is the impulse momentum theorem. So it says that to change momentum, you need to apply a force over a time interval. So force over a time interval equals change in momentum. Impulse is this unit, F times delta T, and it is abbreviated with the letter J, and it is force times delta T, and it has the same units as momentum, which is kilograms times meters per second. Okay, if you're not sure about that, you can think that the units of force here are newtons, which is a kilogram meter per second squared, and then if you multiply that by 1 second, which is the unit of time, the second cancels out, and we're left with kilograms times meters over second. Now, that's the same unit as momentum. So what's the implication of impulse? Well, a lot of things. For example, when someone is jumping in the air and they're on their way down to the ground, when they land, they bend their knees. Right? Why do they bend their knees? Well, you bend your knees because you want to increase the time over which you're applying the force. And if you increase the time, it doesn't take as much force to slow you down. Another example of this is taking a punch. If someone gets hit in the face, you turn your head. There's a saying in English, turn with the punches, right? If life throws you a punch, turn your head with the punch. And the reason you do that is because you make the time very big, which allows the force to be much smaller, and it decreases the force, so it's not as painful. Here's an and we can see here that a fist which has an initial velocity, so an initial momentum, and it comes to a stop, right? So its momentum goes to zero. That change of momentum is stopped by the force of this man's face. But what he did, and we watch this again, he turned his face with the punch, and in doing so, he increased the time the fist was slowing down. And by increasing the time, right, if we look at this equation, by increasing the time, it decreased the force. So if the time is increased, the force is decreased. Well, if change in momentum equals force times time, and we've seen examples where increasing time decreases the force, right? And the reason that is let's think about the fist punch, right? Let's say that fist has a mass of 1 kilogram, and the velocity of the punch is 100 meters per second. It's not that fast, right? But so we see that the momentum initial is 100 units, so 100 kilograms per meters per second. The final momentum of the punch is 0 kilograms meters per second. So delta P for the punch is 100. Okay? So since this is 100, let's say the time that the fist is in contact with the punch is 3 seconds. Okay? Actually, let's make it even something easier mathematically. Let's make it 5 seconds. Right? Really can turn your head. Then the force would only be 20 newtons. Right? So if you turn with a punch or roll with a punch, it really decreases the force. But let's say instead of 5 seconds, let's say that the time that the fist was in contact was only 0.1 seconds. Now the force would have to be 1,000 newtons to give you the same change in momentum of 100. And so now if the punch is very quick and the head doesn't roll with a punch, so the force is spread out over time, the force is much greater. So there are situations where it's beneficial to decrease the time that the force is in contact so as to increase this force like we saw here. And here's an example here. This is the world record for brick breaking by a karate expert in Michigan.
Come on, Kay! 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 Come on, Kevin! 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 Go! 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 You got it, Kay! Come on, Kay! Come on, Kay! World champ! World champ! Hit those bricks!
Try a problem here this is from the book. This is page 201. And this gives us a chance to practice our momentum impulse theory again. So here's the situation. We've got a 1,400 kilogram car moving westward with a velocity of 15 meters per second. And it collides with a utility pole that is brought to rest in 0.3 seconds, right? So let's set this up, and we'll first here write our knowns. So what I know is I know the mass of the car is 1,400 kilograms. I also know that the car has a velocity initial of 15 meters per second, and that is east or west. So that's going in the westward direction. And the time, it's brought to rest in a time of 0.3 seconds. So find the force exerted on the car in the collision. So here's our car. Car's heading this way, and here's our pole. And of course, when it hits the pole is going to apply a force back on the car, and we need to find out what that force is, right? So we need to find the car's change in momentum, because if I know the car's velocity is 15, when it hits the pole, it's going to be 0. So I know the car has undergone a change in momentum, right? And that change in momentum is equal to the force times the time. Well, how do we write this change in momentum? Well, change in momentum, we could say, is mv final minus minus m times v, right? Mass times velocity initial. So the final velocity minus the initial velocity, that's the change in momentum, and that equals the force times time. Well, the final velocity of the car is going to be 0, because it's going to have a velocity of 0. All right, so that's a momentum of 0, and then that is subtracted from the mass of the car, which is going to be 1,400, times the initial velocity, which is 15, and that equals our unknown, which is our force, times time, but in this case, time is 0.3 seconds. So now all I have to do is solve this, and when I solve this, I get a force value of negative, and I'm going to round this up, of 70,000 newtons. The negative tells me that the force is in the opposite direction that the car was moving, which tells me that this force is in the east direction. So we could also say this force is 70,000 newtons east, right? All right, so that's how you apply the force momentum theory in a problem. So let's take a look at another situation that we can apply the force momentum, the impulse momentum theory to. Here's two trucks traveling down the road. They have the same velocity, heading east. This truck is empty. This truck is twice as heavy. It's loaded with bricks. They both slam on their brakes. And the question I'll have you is which truck will take longer to stop? Well, if you answered the loaded truck, you're right. The skid marks on the loaded truck will be twice as long as the skid marks. Whoop, that's not twice as long. Of the empty truck. Why is that? Well, that's because this truck has twice the momentum as this truck. Why does it have twice the momentum? The velocity is the same, but this truck has a mass that's twice as much. And so since its momentum's twice as much, then the time it takes to stop that momentum has to be twice as much as well. So it's going to have twice as long as the skid marks. Let's look at it mathematically. So here's the sitch. You can read the problem here, but we've got a 2,240 kilogram car traveling west, and it's going to slow down from 20 meters per second to 5 meters per second. How long does it take the car to decelerate if the force in the car is 8,410 newtons to the east? So let's do our known here first. Our knowns, right? We know now the mass of the car is 2,240 kilograms. We've got the V initial is 20 meters per second. V final is 5 meters per second. We also know that the force on the car is 8,410 newtons. So it looks like I'm going to apply again this equation, the impulse momentum equation, that the change in momentum is equal to F times T. Okay, our change in momentum is mv final minus mv initial, right, equals F times T. So now we can solve this for our time, right? So what's our momentum initially? Well, that's going to be 2,240 kilograms times our initial or our final velocity, which is 5 meters per second, minus 2,240 times our initial velocity, which is 20, and that's going to equal our force, which we know is 8,410 newtons times our time. Well, now I can solve this for t. So go ahead and plug and chug, and let's see what t is. Set this up and solved it, you would get a time of 4 seconds. Awesome. So the second part of the question says, how far does the car travel during this deceleration? So any questions involving distance and acceleration, that's a season 2 equation. So this right here, we're going to have to dip down back into our season 2 equations. And in our season 2 equations, we had an equation that involved distance, time, and velocities. If you remember, is 1/2 VI plus VF times delta T. So we can use that equation here to find for our distance. And now something we should have done before when we were defining our velocities here. In momentum problems, right, momentum impulse problems, any problem involving momentum, since momentum is a vector, we need to define a direction as positive or negative. So let's define west as positive and east as negative. That's fine. So in our equation down here, when we put our velocities in, both velocities are to the west, so they're both going to be positive numbers. So we're going to get delta x equals 1/2, and then that's going to be 20 plus 5 times delta t of 4 seconds. And this gives us a stopping distance of 50 meters. So it takes 50 meters for the car to come to a stop. In case you're wondering, this is actually how accidents, when the cops study accidents that happen on the road, they do look at the skid marks to work backwards to figure out how fast a car was going. We'll actually do a problem like this in this unit. Hope that was fun.